the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
All right, we're back here working on the definition of a limit, the precise definition of a limit, in fact. And here's where we, as stated on this page, dive into the deep waters, because this is a true definition of a limit. Now, I'm going to kind of cite the definition itself, and then we're going to dig into it a little bit more. So the true definition is as follows. Finite limit at a finite point is really what we would call it, because there are 4 different versions of a definition of a limit. Actually, some would argue there's more or less, but I think of it as 4 different groups of definitions of limits. And this is the one where your x value is approaching a finite value or a finite point, and the function value is approaching a finite value as well. So a finite limit, which is the function value, and at a finite point, which is what the x value is approaching. So here we go. Let f be a function defined on a delta neighborhood, and that should, if that's not familiar to you, it's because you probably have not watched one of my previous videos in this series on limits in calculus. But a delta neighborhood is just an open neighborhood centered at something. Here we're centering it at x equals a. Not only is it an open neighborhood, it's a punctured open neighborhood, which means x equals a is not even in that neighborhood. So I'll just draw that down. So we have some neighborhood that's open. It's centered at a, but doesn't need to actually exist at a, and in fact doesn't exist at a. So let f be a function defined on that neighborhood there, centered at a, where f need not actually exist at x equals a. Then we say that the limit as x approaches that value of a for our function is equal to L if for every epsilon greater than 0, there exists some positive number delta such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. Now, that alone tends to be very intimidating to students. So let's kind of parse this out a little bit. First of all, what we're saying here, the limit as x approaches a, oops, that's not what I wanted. The limit as x approaches a of f of x is equal to L. Let's just focus on that, because that's really what the limit is, right? That's what we're talking about. So x is getting super close to a. That's why we say x is within some very small neighborhood of a. It's very close to a. And that neighborhood is of radius delta. So this is a plus delta. Let me zoom in so you can see that. And this edge over here is a minus a delta. It's a symmetric neighborhood. As x gets really close to a, our function values, here's our function, let's just pretend. Our function values get really close to some height. And in fact, the way I've drawn that function, it's not very exciting. So let me put something that still doesn't look very exciting, but it's actually more apropos for what we're doing. So as x gets super close to a, you'll see all of these corresponding y values get really close to a specific height. And let's pretend as though that specific height is a height called L. So what this definition, or basically what the limit truly is saying, is that as long as x is super close to a, what this notation means, I think a lot of people get lost in that notation, but what that notation really means is x gets really close to a. How close? Within a delta neighborhood of a. That is, it's within this neighborhood, symmetric neighborhood about a. It's not going to exist at a because that absolute value is strictly greater than 0. That strictly greater than 0 right there, that implies that x will not actually equal a, because if x equaled a, well, then it would be 0. So we're really specifically saying here that x cannot actually be a. So we have x values really close to a, but not at a, which means we have x's within that highlighted neighborhood, except for at the center, which my highlighter kind of went over. Sorry about that. And we're saying as long as x's are in that neighborhood, then their function values are really close to L. Again, if you don't know that absolute value, what that absolute value means as far as absolute value of something minus something, please go back to my previous videos in this series where I talk about the fact that the absolute value of A minus B is just the distance between A and B. So this absolute value notation right here is just the distance between your function and your limit. So we're saying our function's really close to our supposed limit. How close? Within epsilon of it. Or in other words, within an epsilon neighborhood of the limit. So if I were to build a little neighborhood, remember the x-axis, we have this big old delta neighborhood I drew out here. And the y-axis will have something very similar called an epsilon neighborhood. This is L plus epsilon, and this is L minus epsilon. So what we're really looking at here, and I'll just kind of jog that over here, is that we have some, and I'm going to highlight that, we have some band there. Let's see, oh, no, that's way too thick of a highlighter. I was hoping that I can get a really nice highlighter. Maybe that one would work. Yeah, okay, that's perfect. So we have this bar here, and this is kind of called an epsilon band. Well, that's what I'm calling it. I don't know if anybody else calls it that, but that's what I'm going to call it. So we have this epsilon band, and in that epsilon band, you can see our function exists in there. There it is right there, right? So what I want to find out is, what is the delta neighborhood down here? Oops. What's the appropriate delta neighborhood? How tight do I have to make that delta neighborhood so that all the x values in that delta neighborhood map only to within that epsilon bar, right? That horizontal epsilon highlighted bar. And you can see the way I've drawn my delta neighborhood right now, it's way too wide. Because if you look at this, if I take a look at, for example, this x value, it'll map up to this point, which is not within that epsilon bar. So I would have to tighten up this delta neighborhood. So let me just do that. I'm going to actually erase all this, and I'm going to make a tighter delta neighborhood. So let's see. Let's pretend again that maybe I'll call this my x-axis just because I can draw a straight line right there. It's a little bit easier. And this point right here is A. And I just want a symmetric neighborhood about A such that all x values within that neighborhood map to y values on the function within that little red horizontal barred region. So this looks like a fairly safe neighborhood. If I called this distance between A and this edge, if I called that distance delta, so this distance right here is a distance of delta, so therefore this distance is delta, then it goes from A minus delta to A plus delta, and if you look at any point within that neighborhood, it looks to map successfully to within those red bars. Turns out that the delta neighborhood is not unique. You could see that if I tighten up or ratchet up that delta neighborhood even smaller than what I have just written, it will still satisfy the constraint of needing to map into that red horizontal region. So if I really chose a very small delta neighborhood, again, about A, it still satisfies that all of the x values within that delta neighborhood map into the epsilon neighborhood. And that's really what the true definition is saying. So let me go back down to the true definition here and read it one more time, because maybe a second time through might make sense before we go to the visuals, right? So we have a function. It's defined on a delta neighborhood for a set of x values. It doesn't need to be defined at the center of that neighborhood. And then whenever you read that the limit as x approaches a of f of x is equal to L, they're really saying that no matter what epsilon neighborhood somebody hands us, we can find a small enough delta neighborhood that all x values from that delta neighborhood will map into the given epsilon neighborhood. Now, that's the critical piece. It's a given epsilon neighborhood. So we have to assume somebody handed us that. That being said, let's go ahead and jump over to a visual of this. So as you're looking at this visual here, I just have a function. This function is actually 2 raised to the x power. This is on Desmos, and I will include the link to this in the comments section or the description section. But if you take a look at this, somebody has given us a function, 2 to the x. And by the way, I could change these functions all day long and make them anything I want, but I'm just specifically focusing on 2 to the x. And what somebody is likely saying is that the limit as x approaches 1 of our function 2 to the x is going to be 2. The limit as x approaches 1 of 2 to the x is 2. That should make sense to you. As x approaches 1, 2 to the x approaches 2 to the first, which is 2. Okay, I get it. But just saying that's true is not enough. It's just not enough to say, well, it's true because as x gets close to 1, 2 to the x gets close to 2. That is good enough, I suppose, if you're in algebra. But if you're in calculus, you need to be more rigorous with that statement. So to be more rigorous, you have to say, well, all right, suppose somebody hands me an epsilon neighborhood, kind of like this guy right here. Somebody has handed me a neighborhood. It looks to be about a neighborhood of size 0.5. Goes from 1.5 to 2.5. So the neighborhood itself has a width or a radius of 0.5. That's a pretty large epsilon neighborhood, to be very honest with you. My job is to find an appropriate delta neighborhood. So I need to clamp down this gray region that's surrounding 1. It's symmetric about 1. And so I would like to clamp it down so that all x values from this x-axis here map directly into this red region. Right now you can see that's not the case. If I grab an x value over here, it'll map above the red region, and therefore you see that's not good enough. Same thing on the left hand side. If I grab an x value that's less than 0.5, let's say way over here, and plug it into my function, it maps to a y value that's outside the red region being the epsilon neighborhood. So I need to tighten up my delta neighborhood. You can see none of these neighborhoods so far are good enough until we get around here. Actually, notice right there, all of a sudden that side is now good enough, but the right hand side still not good enough, because again, you take an x value from way over in this extreme edge and it will map to a y value outside of that red band. So I need to tighten up that delta even further, and there we go. Now notice every x value that I grab in this delta neighborhood, the delta neighborhood's the gray neighborhood, gets mapped to our function on a y value that's within the red neighborhood or the epsilon neighborhood. So it gets mapped to a y value within the epsilon neighborhood. And if you heard a big, like loud bling, it was because somebody emailed me. So I'm going to turn off that. There we go. All right. Something else I want to mention here. If you find a delta neighborhood like this, you can actually tighten that up even further. If a wide delta neighborhood works, then a smaller delta neighborhood will also work. So once you find out that, for example, delta of size 0.3 works, then a delta of size 0.2 will also work, and a delta of size 0.1 will also work. So there are actually an infinite number of delta neighborhoods that'll work once you find your entrance into the right delta neighborhoods. Now, I do want to actually scroll over to the side here and showcase the code. So the function is 2 to the x, and I have a centered at 1. The definition is that the limit as x approaches a of f of x equals L means that for any given epsilon that's positive, so we can set our epsilon here, or somebody hands us an epsilon. I handed you this epsilon. That's the critical part. Somebody hands you an epsilon. Then we have to find a delta based upon that epsilon such that as long as the absolute value of x minus a is positive but less than delta, then the absolute value of f of x minus L must be less than epsilon. And this was what I was talking about earlier, that really this language right here is just saying x is super close to a. How close? Within delta of a. So x is in a delta neighborhood of a. And that would mean that f of x, the function value of x, I didn't know I could drop an image there. The function value at x is really close to L. How close? Within epsilon. So this is what I'm saying here. Another way to think about those last two lines, these last two here and here, is as follows. So there exists a delta greater than 0 such that as long as an x value is within the delta neighborhood of a, then its function value, f of x, is within the epsilon neighborhood of L. Again, let me read that. As long as an x value, and actually, I think I can scroll this over. You could see this right now. As long as an x value is within the delta neighborhood of a, as long as we've selected or found the appropriate delta neighborhood, then the function value of whatever x value we have within that delta neighborhood should land within our epsilon neighborhood. There you go. That's exactly the true definition of a limit. Now, something you need to understand, proving that this limit works for epsilon equals 0.5 is not good enough, because then the next person who enters the room is going to say, well, what about an epsilon of 0.168? And now you have to do all your work over again. Oh, let me tighten up that delta neighborhood. Boom. Now somebody might say, well, I know how to beat the game. I'll just make a super small delta neighborhood. Now somebody can't beat me. But trust me, somebody can beat you. They can make a delta small enough to beat your finite delta that you created. So the idea behind a true proof is to make the statement work for any given epsilon. Let me say that again. You want to keep it as general as possible so that no matter what epsilon somebody hands you, your delta will automatically adjust without you being in the room. It'll just automatically adjust accordingly. And that is the trick to an epsilon delta proof for a limit. So going back to our definition here, there are a few things I'd like to talk about before we jump into the deep waters of actually proving. The proofs are not too terrible once you get used to them, but there are some things we need to talk about. First and foremost, kind of the cornerstones of this whole entire conversation. Delta, the delta neighborhood, the wiggle away from the center of the x neighborhood, and epsilon, which is the wiggle away from the y value, the limit value L. Those must be both strictly positive. You will not believe me. Well, maybe you will believe me, but people will often go through proofs and end up with epsilons being negative, and they seem fine with it. And that is not okay. That means you're not truly understanding the epsilon delta proof. Delta and epsilon are just radius, or radii, since that's a plural, right? So they're just radii away from some center. So they have to be non-negative. And specifically in calculus, these neighborhoods are punctured open neighborhoods, so they are positive radii. All right. So what do I say here? When proving that a limit is correct, you must not only state, yes, this is critical, you must not only state that delta and epsilon are positive, but you must also use those facts within the proofs. If you don't use them within the proofs, then you're assuming that they don't matter, which they do. And we will see this in our examples in a different video. Now, again, I hate to read just off a piece of paper, but I actually wrote all of this. And so it's kind of my language. That's just how I talk. So I often find that a more straightforward definition to work with while retaining the rigor of the original definition is the following. And I personally will be using this version of the definition exclusively for the rest of the course. If you're done in my class and you're just watching this on YouTube, then you don't have to freak out. If you're in my class, prepare to freak out a little, but actually you get used to this notation. It's the same exact definition. Let f be a function defined on a delta neighborhood centered at A, where f need not actually exist at A. Then this notation, limit as x approaches A of f of x equals L, means the following. And then a bunch of symbols. So let's clarify all this. This is symbolic logic. If you do anything, if you take a symbolic logic course, take a philosophy course, take a I'm trying to think of the name of the course, like a finite mathematics course and stuff like that, you will run into these symbols all the time. That upside down capital A right there, that means for all. For all. It also means for each and for every. And so I say that down below, where the upside down capital A means for all or for each or for any or for every. It doesn't really matter. The backwards capital E means there exists or there is. Okay. So far we are saying for all epsilon greater than 0, there exists. Mathematicians notoriously love to shrink language down. If a true mathematician writes a textbook, it is a minimal number of pages with a maximum number of uses for substitutions for language. So, for all epsilon greater than 0, there exists a delta greater than 0. This backwards little container symbol is what most people would call it. That is actually up for grabs as far as, or up for contention. It's a contentious symbol because some mathematicians do not like that symbol being used for the words such that or so that, and some mathematicians will actually just use ST, and that's fine too. I don't care. But the way I learned it, both in undergrad within the UC system and in my graduate work, when I used it there, and when I talked to when I worked in the program there, we use that notation for such that, and so I think that most people do use it. Okay, so again, reading this, it says for all. Actually, let me highlight as I read. For all epsilon greater than 0, there exists a delta greater than 0, such that 0 being less than the absolute value of x minus a being less than delta implies that the distance between f of x and L is less than epsilon. Now, I'm going to go ahead and switch back a page in a moment, but I want to read that again really quickly. For all epsilon greater than 0, there exists a delta greater than 0 such that, and then you have this last little bit that's the same in both definitions. Let me hop back. For every epsilon greater than 0, there exists a number delta greater than 0 such that. Now, I don't like writing all of that language, so instead, I use this language. For all epsilon greater than 0, there exists a delta greater than 0 such that. It's the same language, and it's probably better that you get used to that now. To keep this kind of clean, I'm going to erase this language here because it's all defined in this definition right below in the sentence below. I just wrote it above out of habit, but honestly, it's right down there. Now, like I said, while initially very confusing, you get used to seeing statements like these in mathematics, logic, and philosophy courses. Moreover, they condense the language nicely and allow you to see patterns. For example, the entire definition starts with the assumption that we've been handed an epsilon greater than 0. It is a pattern that I would love you to notice, that the very first statement is, somebody handed me an epsilon that's positive. That's critical to note. And this is the second point. There's several important points here, and this is the second one. In general, epsilon is either explicitly handed to us or We can assume it has been given to us, and our job is to find the related delta neighborhood to satisfy the definition. Remember, the epsilon neighborhood that we've been handed gives us that vertical, or I should say that horizontal bar. And our job, so somebody walked in the room and handed us that epsilon neighborhood, our job is to tighten up the delta neighborhood so that we do a great job. We have to find the related delta. And by the way, delta relies upon epsilon. So that's critically important. Often it does, almost always. And that's what I'm saying on this next statement here. And this is actually the next page I just kind of jumped over. But the third thing to note is that epsilon, whether explicitly stated or not, is almost always infinitesimally small, and it usually relies, well, I didn't state it here, but it usually relies upon delta. So nobody's going to walk in the room and say, I bet you can't find a delta neighborhood for an epsilon of size 1,000, because that's a huge horizontal bar. They're making it too easy. They will make epsilon infinitesimally small, very, very small. So going back to our visual, more often than not, they're not going to give you some big old epsilon neighborhood like this. They're going to try to really catch you by giving you a super small epsilon neighborhood. And your goal is to zoom in, which you won't be able to, but to find the correspondingly small delta neighborhood so that you do great work. Unfortunately, the way I have this coded, I can't get that small with this delta. I'm very close to it, but I can't get exactly that small with this delta. There we go. So anything else I have to say about that? Epsilon can be considered to be infinitesimally small. Delta, on the other hand, need not suffer that constraint. Delta sometimes can be very wide, or very large, I should say. But in general, you're often going to have a small delta as well, but it doesn't need to be that way. And finally, this is what I was saying. It won't take long for you to realize that delta always relies upon epsilon. Even if it doesn't explicitly rely upon epsilon, it is still considered to be a function of epsilon. So this is the last thing I need to say. And now the true definition without all the fluff in the words, this boils it down to the best definition of a finite limit at a finite point, the official one. Assuming f is defined on a delta neighborhood, but not necessarily at x equals a, and I should have said delta neighborhood centered at a, but not necessarily at a. The limit as x approaches a of f of x equals L means, I'll highlight as I go, for all epsilon greater than 0, there exists a delta that relies upon epsilon, which is greater than 0, such that as long as x is super close to a, how close? Within a delta neighborhood of a, then f of x is super close to L. How close? Within an epsilon neighborhood of L. That is the true and really succinct definition of a finite limit at a finite point. Notice that once we remove the symbolic descriptions, this definition is succinct. So in the next video, we're going to use this definition to prove that limits are true. Not just one limit, but several.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.